Hey everybody, welcome back from spring break, and we'll press on to finish this last couple of chapters. We probably need to go back and refresh what we did on Friday, since we've had 9 days to forget everything we learned. We had started the chapter on two sample t-tests and two sample t-intervals, had looked at the differences when you compare two independent samples versus when you just deal with one independent sample, or one sample in general. So we learned how to do a confidence interval on Friday, but we've slept since then. So we'll start with another confidence interval practice question, and then we'll move on into how to run the hypothesis test. So you have this problem in your notes about some archaeologists who have this theory that when ancient Egyptians interbred with other immigrant populations over thousands of years, they think that their body structure might have changed. And so they took 30 skulls of ancient Egyptians, and they looked at just the males, I guess, so that they could have some consistency. And then they took 30 of them from about 4000 BCE, and then 30 others that were dated for about 200 BCE, and compared the difference in how broad those skulls were, the size of the skulls. So this actually comes from a study published in the Ancient Races of not even sure what that is, from Oxford University back in the early 1900s. So some fairly old data, old research. So we start with the question, create a 95% confidence interval for the difference in mean skull breadth or diameter, how broad, between those two eras, those two time periods. So we have this big chunk of data, and you have a couple choices. You can pause the video and put that data into your calculator so that you can follow along and push the buttons, and then pick back up and we'll go from there. Or you can watch me push buttons, entirely up to you. So I already have that data in my handy dandy Inspire, all ready to go, and I'm going to be ready to write down all the mechanics, all the number crunching that I need, because I've already got my data in. So first thing we want to do is check conditions. Nowhere in here did it say that conditions had already been met. That means we have to actually check those. So we have a spot to do that on the next slide. So with two samples from two separate populations, we always have to check a fourth condition, that the two samples or the two groups are independent. So we want to make sure we don't forget that one. So as always, we're going to start with randomness. In the stem of the problem, it didn't say that they had random samples of skulls. They had skulls that they could find. So it's not like you can just go out and select a random sample of 4,000-year-old skulls. So the best we can do is argue that the samples of skulls that they have for both groups are representative of all Egyptian male skulls of those time periods. So we might say something like, assume that the 30 skulls from each era are representative of all skulls from those eras. We want to be really sure that we include both groups. When you check this condition, check both groups. You can do it in a single sentence. Make sure you talk about multiples. There's no reason for us to believe that this is not true. And then we check for independence within the samples, or the less than 10%. So there were definitely at least 300 people, 300 Egyptian males in the earlier time period, and at least 300 Egyptian males in the later time period. So we can either assume that the skulls in each era are independent of each other, or that they're less than 10% of the population. And you just choose one. So let's say that 30 is less than, and make sure you always include this number. You're talking about the sample size. This is a sample size check. This check is about making sure your sample is not too large. And so some of you are still trying to kind of fudge on this one, not sure you even know that you're checking sample size. You have to make sure you communicate that you know that you're checking a sample's size. So 30 is less than 10% of all possible skulls from each era. And since they both had the same sample size, you can wrap that into one statement. If you'd had different sample sizes, you would need to mention both of them. So our sample size is not too large. Okay, then we want to also make sure that our sample size is not too small. So this is our large enough sample check. And 30 is the magic number that central limit theorem needs to guarantee a nearly normal sampling distribution. And some of you are just saying 30 is a large enough sample. You need to back up that with the central limit theorem. That's going to be expected on the AP exam. So 30 is a large enough sample size for both eras, and we'll say central limit theorem guarantees a nearly normal, or you could say approximately normal, but approximately is a long word, distribution of samples. I'm just going to say nearly normal distribution. Yes, we're using a t-model when we actually calculate the confidence interval and run the hypothesis test. But t looks a lot like normal when the sample size gets large. The normality check, this is a check for, does it actually look normal? Is it the right shape? Is it bell-shaped? Unimodal symmetric, and that's the check that we need. Now, we have to add the extra check, and it doesn't matter where you add it as long as it's in the list somewhere, that the older skulls and the less old skulls are independent of each other. So let's assume that skulls from 4000 BCE are independent of skulls from 200 BCE. Now, for those of you who want to write 5 or 6 word sentences and get it done, it is time to wake up and smell the coffee. It doesn't get it done. This is the longest part of the process. Checking conditions is the most important piece of the puzzle, because if they don't check, nothing else works. You can't do the mechanics. You can't draw a conclusion. There's no way to back up your number crunching. You have to take the time to do this thoroughly. And if you are making it any shorter than what I'm writing down, you are not getting it done. You are not getting all your points on AP exam day. You get one shot at a college credit on this. Make it count. Be thorough. Which means you need to practice being thorough so that it's a natural thing to do on exam day. Well, there's no reason to believe that any of these aren't okay, so we are going to conclude that a t-model is appropriate, or can be used, however you want to say that. And we're going to create a 2-sample t interval. Okay, the longest part is finished. Checking conditions is at least one of your 4 points. If you name your procedure at the end of your conditions, that's usually your 2nd point. So this page just got you half of your point value. Out of a 4-point question, this is going to land you 2 of those points. Make it count. Okay, so now we do mechanics and write a conclusion. We can squeeze those on a single slide because that's the shorter piece. So the mechanics we've not seen since before spring break, so we'll have to kind of go back and look at that. I'm going to pull out a copy of one of the earlier slides. We are looking at this, oh, that's a test. That's not the right slide. Mr. Nice does not have the right slide out. Nope. And I don't see it in my pile. So let me just write it down. So for the mechanics, we are going to take the difference of the two groups, y bar of the first group minus y bar of the second group. That's the difference of the two means. That's your point estimate of the difference. And then you're going to add and subtract a margin of error. So this next little piece is your margin. To calculate the margin, you need to know how big, how many standard deviations out you're going to go, standard errors technically. So you need a T star with some really goofy number of degrees of freedom. There's a nasty little formula that was in a footnote for the degrees of freedom that we will never ever use. We're just going to let the calculator do it for us. And then multiply by the standard error formula, which is in the blue book, that says take the square root of the standard deviation squared of the first group over the size of the first group, n sub 1, plus the standard deviation squared of the second group over the size of the second group. So there's our formula. For the mechanics, we want to substitute in numbers. Very much like what we've been doing on Schoology with actually substituting those numbers in and showing the formula. If you show the formula with all the numbers substituted in and then show your final interval, that will give you full credit for your mechanics. Be very, very sure that somewhere in the process you communicate how many degrees of freedom that you have, even though the calculator is going to calculate that for you. Now, we can't put any numbers until we have numbers. We don't have any summary statistics yet. We were given the raw data. So we'll have to let the calculator do all of that work. So we've got our data in. We can either do it here on this screen, on this spreadsheet, or we could do it on a calculator screen. I prefer the calculator screen because it's a little easier to read. So I'm going to add a page, add a calculator, and run my analysis here. So menu, number 6 for statistics, number 6 for confidence intervals, and I need a 2 sample t interval, which is option number 4. This time I have the data, not the stats, so I'm going to leave that on the data option, and OK. And then I just have to tell it the list. So list 1. Now I've got to decide whether I'm going to do old minus young skulls or young minus old skulls. Here's what I typically do. Whatever order they're in the table that I'm given, I usually try to maintain that order because I'm less likely to switch things up accidentally. So in the left column of the table were the 4000 BCE skulls. I'm going to let that be group 1 because it was in the first column. So I'm going to refer to the oldest here, which is what I called mine, whatever label you used. And then the list 2 is the ones from 200 BCE, which are the old ones. They're still old, they're just not as old as the other group. But make sure that you establish a way to hang on to which ones are which. Okay, and the frequency of each list is 1. Each number in your list counts 1 time. If you have a list where you have all of your values and then a separate column for how many times to count each of those, the frequencies, then you would put those lists here. That typically is never going to happen. And then we want 95% confident. That's what we were asked for. When we're asked to pull, we always say no. If we're given the option, it's always a no. If we have to pull with proportions, we don't get the option. And click on OK, and we have lots and lots of information. Okay, so the first thing we need to do is start substituting into our formula. So the first thing we need are our means, and they're in the same order here that I want to use. So the first group has a mean of 131.3. I'm going to just round to 7, minus the second group has a mean of 135.63, plus or minus T star, and degrees of freedom the calculator has computed to be approximately 54.97. So I'm going to put that on as a subscript. If you make that a habit, then you have clearly communicated that you know what the degrees of freedom are, and that covers your backside for that communication. If you don't put it on that subscript, it's just a label. It doesn't do any kind of calculations. It's just a label. If you don't put it there, somewhere off to the side, somewhere in all your mechanics, you've got to write DF equals and communicate what that is. All right, times, and then this square root that calculates the standard error is next. Excuse me. Ooh, my allergies are acting up. Okay, so we need standard deviation or standard error. This is technically standard deviation of our sample of the first group, which is 5.129-ish. I'll say 5.13-ish squared over N1 is the size of group 1, that was 30, plus S for group 2, that's 4.04-ish, square it over sample size of 30. So the calculator's already done all the number crunching for us, all in one step. We just have to put the right numbers in the right spots in the formula. If you write this down on AP exam day, either writing it on your paper and uploading the picture, which is probably the safest route with the time frame that you're limited to on AP exam day, or if you type it in. And I have no idea what that's going to look like. Hopefully over the next few weeks we will see some sample work on AP Central that we can try out and kind of see what maybe those tools might look like. More about that later. So for now, let's just move on. So notice that I didn't actually crunch that T star. I don't know what that actual number of standard deviations from the mean is. I'm not worried about it. On the two sample ones, because it's so heinously messy, we don't worry about communicating that. They will not require us to put a number in there. So now let's go back and we'll click up, and we'll see the mean difference is actually about 4.27 millimeters. Which means the oldest skulls are actually about 4.27 millimeters bigger, nope, said that wrong, smaller on average than the less old skulls. So there's evidence here that over the course of all those eras, their heads got bigger because of all the intertwining of other ethnic groups. So let's go ahead and jot down our interval. We have a lower bound of negative 6.66-ish, okay, and an upper bound of negative 1.88-ish. So the entire interval is negative, which implies that oldest minus old is always negative, which means the old is bigger than the oldest. Zero's not in here, so it clearly leads us to believe that heads got bigger, skulls got bigger over the course of the eras. Okay, mechanics are done. So let's move on to conclusion. We are 95% confident that the mean skull breadth, that's a crazy word to try to say, around 4000 BCE was between 1.88 millimeters and 6.66 millimeters smaller, there's our comparison word that we need, than the skulls from the 2000 BCE era. Super important. Make sure you communicate a level of confidence. A couple of you are still kind of skimping on that on quizzes and tests. Your first 4 words should be, we are something percent confident. Every single time you do a conclusion, make sure that the word mean or average is making an appearance. It's not about individual observations. This is about the mean of a sample. It's about, well, technically, we are estimating a difference in the means of the entire populations here. And make sure there's a comparison word in there. You're comparing 2 groups. And if those 2 words, mean or average, either one will work, and some comparison word, if those are not there, chances are you're not going to get your full point for this conclusion. Okay? And we want to get our points. Alright, well that was kind of long, but it had been a while since we've done anything for this chapter. So let's move to the very last problem. We're going to take one look at a hypothesis test for 2 independent samples and see how that looks different from the confidence interval, how that looks different from the 2 proportions that we did in the last unit. So let's go to the medical field and dig into this one. Resting pulse rates for a random sample of 26 smokers had a mean. I see that word mean. When I see the word mean, I know that I'm solidly in quantitative world, and whatever procedures I have to do are going to be using T-models of 80 beats per minute. I also know I'm in quantitative world because I have units, beats per minute, and a standard deviation of 5 beats per minute among 32 randomly chosen non-smokers. So there's our second group. The mean and standard deviation were 74 and 6 beats per minute. Both sets of data were roughly symmetric and had no outliers. So that's our check for normality right there. They're giving us what we need to check for the normality. Because one of our groups is smaller than 30, this is going to cover our backside since we don't have at least 30 and we don't have the data to look at a picture. Both sets were roughly symmetric, no outliers. Is there evidence of a difference? Is there evidence means do a hypothesis test. Always means to do a hypothesis test. Of a difference, we're going to subtract some things, in mean pulse rate between smokers and non-smokers. Okay, hypothesis test, step 1 is always to define parameters and write hypotheses. Some of you still don't know what it means to define parameters. At least that was the evidence that I saw on the last quiz, or even the last test. You don't know what that means. Parameters are mu or p. Those are values that we're proposing for the entire population. So we're going to look to compare the mean pulse rates for all smokers, the mean pulse rates for all smokers, and the mean pulse rates for all non-smokers. That's what we want to compare. So let's start by defining those 2 parameters. We're looking at assumptions for entire populations, so this should be a Greek letter. So let mu be the mean pulse, that's an L, pulse rate for all population smokers. Oh, okay, hold on. Now I've got to do smokers and non-smokers, which means I probably need subscripts. 1s and 2s work, but S for smoker and N for non-smoker, probably more practical choice. So I'm going to do a subscript of S for smokers, and then we'll let mu of N be the mean pulse rate for all non-smokers. Do not use Y bars here. We're talking about populations. Hypotheses are about the population that we don't know. We know the sample statistics. We don't need to hypothesize about those. So stop putting Y bars in your hypotheses. Okay, they don't belong there. If you put Y bars in your hypotheses, or if you put statistics in your hypotheses, if you start talking about 26s and 32s and 80s and 5s, if you start throwing those numbers in here with Y bars and S's and N's, you can kiss your point for hypotheses goodbye. It's not going to happen. Okay, these have to be correct, which means you define your parameters. Parameters are just mu's. They're Greek letters in mean world. And you write your hypotheses. So the null hypothesis tells us something about the difference in mean pulse rates for the two groups. So I can do either smokers minus non-smokers or vice versa. It doesn't really matter. I'm just going to pick smokers minus non-smokers. So I'm going to argue that the difference in the mean of smokers and the mean of non-smokers, a difference is what you get when you subtract, is 0. Unless otherwise noted, we're going to assume the two groups are the same, that they have the same rates, those same resting pulse rates. Okay. On the contrary, there's an alternative hypothesis. We don't really believe they're the same, otherwise we probably wouldn't be running a test. We want to know if there is a difference. So a difference could be smokers are bigger than non-smokers. It could be smokers are lower than non-smokers. So this is a not equal to 0. These are different means not the same. So it could be a greater than or a less than. It's going to be a two-tailed test. So the mean of smokers minus the mean of non-smokers is not equal to 0. On your hypotheses, this is all you write. Do not make a list of numbers. Do not make a list of statistics. That's going to get you in trouble because you're communicating that you don't really know what you're talking about. This is all I should see on hypotheses. Okay. Conditions. Do we have room for conditions here? Let's see if we can fit them. I don't know. Let's try. Okay, so condition number 1, we have random samples. If I go back and look at, random sample, randomly chosen. All right, we're good. So both let me try again. Random samples of smokers and non-smokers were used. All right, do not say assume they're random samples. You're not making an assumption. You know they were random samples, and you need to phrase this in such a way to communicate that you know that they were random samples. Don't put the word assume in here. This is not an assumption. This is a we know it's true. All right, number 2, independence within the groups. So we're going to assume the pulse rates. I'm actually going to squeeze in the independence for the 2 separate groups on this one. So we're going to assume that smokers and non-smokers are independent groups. Okay, so we're going to assume pulse rates of smokers are independent of non-smokers. So that's the extra, the 2 groups are independent check for the 2 groups, 2 sample test. Now we'll go back to our usual independence within the samples. So we either want to argue that the 26 people in the smoker group and the 32 people in the non-smoking group had independent pulse rates, or we can argue that each of those groups are less than 10% of the population. Let's say that 26 and 32, I'm communicating that I know this is a sample size check. Sample sizes can't be too big. Are each less than 10% of all smokers, and non-smokers. Okay, so I'm checking both groups at the same time, and I'm communicating that I'm comparing a sample size to the size of the entire population. All right, there's a fourth one. This is the normality check. This is the shape set. So I'm going to say a couple things. Sample sizes are large. I mean, one of them is 32. 26 is close to 30. And I'm going to add a piece to help with that 26. We are told that both sets of data are symmetric with no outliers. Sampling models should be nearly normal. So we checked for randomness, we checked for independence, we checked for shape, for normality. So we'll conclude that a T-model can be used, and we'll do a 2-sample t-test. The worst is over. That's the long part. Mechanics we can do all in one step. Okay, so let's start with the picture. So this is a picture of the differences of the means. Y bar smokers minus Y bar non-smokers. So if I found lots and lots and lots and lots and lots of groups of smokers and non-smokers and sampled people and compared the differences in the means, I would get a picture that looks like this. All possible sample differences are in this picture. And we proposed in the null hypothesis that the difference was 0. They're the same. The groups have the same resting pulse rate. Now, we need a t-score so that we can figure out where our observed difference in means is. So I need a t-score. This is not a t-star. T-star is a critical value for a confidence interval. This is a t-score that tells us where on this curve we are. It has a particular number of degrees of freedom that I don't know yet. Okay? So I'm going to come back and put that in later, either writing df somewhere on my graph or putting it in the subscript. So I have a formula for a t-score. We start with the difference in the observed means. So that's the y1 minus y bar 1 minus y2 bar that we had in the first part of the confidence interval. So I need the difference of the actual means. Oh, I don't know that yet because I've not crunched any numbers. Oh, yeah, I do. I do know the means. If I go back and look at the original problem, the smokers had a mean pulse rate of 80 beats per minute. And the non-smokers had a resting pulse rate of 74 beats per minute. So we actually do already have those numbers. So that's the observed difference in averages, minus the expected difference, which is 0. And I know some of you are saying, do I really have to write the 0? Yes, you do. This is communication of the big idea. This isn't about number crunching. This is about communicating how to crunch the numbers. And in the denominator, we need the standard error. It's the same standard error formula that we used in the confidence interval. We don't have to pull in means. We never pull in means. We only pull when we deal with proportions, with p hats and p's. So the square root of s1 squared over n1 plus s2 squared over n2. Same formulas we used in the last example. So I go back and look in my original example, and I find out that the standard deviation for smokers was 5. So 5 squared over a sample size of 26 smokers, plus then I need standard deviation of non-smokers. That was 6, square it, over the sample size for non-smokers, which was 32. You do have this formula on an earlier page of your notes. So just a quick peek at that. If you go back and look at this earlier page of the notes, here's your formula right here. The difference of the observed means minus the difference from the null hypothesis over the standard error. And the standard error formula is here. And you kind of squish it all together to make your formula. Now we still don't know our degrees of freedom, and we won't until we actually run the test on the calculator. So I propose, instead of typing all this mess in the calculator, let's just go ahead and run the test so that we can get all of our numbers in one fell swoop. So menu, statistics, number 6, number 7 is stat tests, and we need a 2 sample t-test. So number 4, we want not data. We don't have the actual data, we just have the summary statistics. We don't actually know the pulse rates of the 26 smokers and the 32 individual non-smokers. We just know what their summary was. And so I did smokers as my first group, so X1 and X bar 1 and X1 are going to be the smokers group. So 80 is the mean of smokers, 5 is the standard deviation of the non-smokers, and the sample size was 26. Group 2 is non-smokers. They had a mean of 74, standard deviation of 6, sample size of 32. And then the alternative, we can choose not equal to, greater than, or less than. It was a two-tailed test. We had a not equal to in our alternative. If we're asked to pull, we always leave it a no and okay. And everything we need is here. So let's go up and recover some information we didn't have before. Degrees of freedom. You're either going to want to write them on your subscript of your T, or you could just squeeze them anywhere in your mechanics, but they have to be communicated somewhere. If you do not tell the reader what your degrees of freedom are in your mechanics, or even in your conclusion, if it's not in your answer somewhere, you will not get a 4. It will not happen. Okay, and then we need the actual t-score. So that's been crunched for us. It's 4.15-ish. So we are 4.15-ish standard deviations above the mean. That's really extreme. 1, 2, 3, 4, we're about there. Very little stuff there. And since it's a two-tailed test, we need to get the mirror image. 1, 2, 3, 4. The mirror image over here. We want to know the area in those two tails. That's the p-value, and it's going to be really, really small. So the p-value is 2 times the probability of a t-score greater than 4.15, because we double it. And this p-value right here has already been doubled because we told it was a two-tailed test. So the calculator has already found the area up here in the top tail and multiplied by 2 before it spits out this 1.13 times 10. Oh, you can't see it. Let me scoot that over. Times 10 to the negative 4th. So we should be looking for something really, really small, and 1.1 can't be the correct answer because it's a probability. You can't have probability bigger than 1. So make sure you're looking for that scientific notation detail over here. So this is equal to 1.13-ish times 10 to the negative 4th, or you could write 0.000113 if you'd rather do standard notation. Alright, that's really small. It's nearly impossible to get a sample that extreme if the null is really true. So we're going to reject the null that says the two groups are the same. They do not appear to be the same. Evidence says otherwise. So with a p-value of 1.13 times 10 to the negative fourth, we will reject the null hypothesis at an alpha level of 0.05. It's just a choice I'm making. You can use any reasonable alpha level here, still going to reject. So first sentence has to have linkage of p-value, alpha level, and a decision about the null. Some of you are still writing sort of rogue conclusions here. You need to do it my way to make sure you get the linkage. And by the way, don't put the word linkage in there. That's not your word to put in your conclusion. That's the reader's word for what they're checking for in your conclusion. This is how you structure it every single time. Learn to say that sentence. If everybody says it that way, nobody's going to say, oh, they're cheating. They're going to say, the teacher trained them to all say it the same way. Okay, so don't go rogue on this one. Second sentence is a context sentence. If we reject the null, it means we have evidence to support the alternative. And the alternative is that the mean pulse rates are different. So this statement tells that we have strong evidence that the mean resting pulse rates are different for all smokers and non-smokers. Remember, it's a conclusion about the populations. Try to make sure you squeeze that word mean or average in there somewhere. That's what you're talking about. It's not about individual observations, individual people. It's about the whole group of smokers, the whole population of non-smokers, and how their averages compare. Okay, so I've split up what had been the day 2 homework into 2 separate days to kind of spread that out and give you practice over a bigger period of time, since we're having a little more time to work with than we normally would now that they've knocked off those last 2 chapters. So for today's work, you're going to do page 625, number 7, 9, and 19. And then tomorrow, you're going to add the last piece, which is a couple of extra practice problems, 25 and 27. I know those aren't on this PowerPoint, so there won't be any notes tomorrow. Tomorrow's just an extra practice day. You do have a quiz on Thursday. I'm not thinking right. This is Monday. I've got to get my head on straight here. Tuesday, quiz on Wednesday. Every day just kind of runs in together these days, doesn't it? Okay, so quiz on Wednesday over chapter 24. That's the only thing. Sorry, chapter 23. That's the only thing we'll do on Wednesday. Thursday and Friday, we will do notes on the last chapter that we're responsible for, chapter 24, which means you'll be looking at a quiz the following Monday. Then we'll be ready to review for the last unit exam in the middle of the week. And after that's over, we will be ready to start hardcore review of the entire textbook, of the entire curriculum, and be prepping, 100% prepping for the actual AP exam. All right, so hang in there. We are almost finished with this, and I'm still hoping that I get to see you before the school year is over. Take care and stay healthy.